Welcome everyone. Today, we're going to dive into the cognitive blueprint and introduce you to XSKILL, a brand new framework designed to equip multimodal agents with dual-stream continual learning. Let's start by looking at the core problem we face today, the multimodal bottleneck, which we call stateless execution. Current agents are basically stuck in a Groundhog Day loop. Without memory, they suffer from inefficient tool use, wasting their limited reasoning steps constantly repeating the exact same basic syntax errors. Furthermore, they face inflexible orchestration. They are trapped in single-path execution and simply cannot adapt their tool choices to unique visual contexts or recover when they hit a roadblock. So, why can't standard text log memory fix this? It's due to the visual-semantic gap. A standard text log is blind. If an object detection attempt fails, the log just records no objects found, and the agent will stubbornly try the exact same text-based command again. XSKILL solves this with visually grounded memory. By looking directly at the visual context, the agent gains a crucial insight. For example, the image of these mascots is upside down, allowing it to execute a rotation action and successfully detect the objects. To build a better system, we looked at biology and mapped human learning to silicon. Humans improve through two distinct channels, strategy and tactics. We designed the XSKILL cognitive engine to mirror this. The strategy part becomes our skills. These are structured, reusable blueprints that support high-level planning. The tactics part becomes our experiences, the muscle memory and concise, context-sensitive guidance distilled from prior attempts to handle local decisions and error recovery. Here is how this dual-stream taxonomy breaks down. On the strategic side, we have skills. These handle task-level orchestration and are stored as structured markdown documents, providing reusable tool templates and global workflows, like a standard operating procedure for a specific type of cropped image search. On the tactical side, we have experiences. These operate with action-level precision, using JSON key-value condition nodes to trigger specific condition action responses, for example, enhancing an image if the contrast is too low before searching. The XSKILL framework operates in two main phases, starting with Phase 1, distillation and consolidation. Here, we take raw trajectory rollouts and feed them into our knowledge base model. The key here is that we are abstracting, not just memorizing. The system visually critiques these raw rollouts, merges similar experiences together, and refines lengthy instructions to prevent our memory repository from bloating. This distills the massive amount of data down into separate generalized skill documents and specific experience nodes. A critical mechanism in this first phase is the cross-rollout critique. To isolate the real causal factors behind a result, the system directly contrasts successful trajectories against failed ones. For instance, if one path successfully zooms into an image, but another fails because the objects are too small to read, the system compares them and extracts a clear, tactical experience. If objects are too small, inject a crop or zoom tool before attempting detection. When it's time to actually solve a new problem, we enter Phase 2 and use task decomposition retrieval. Instead of using one raw query, we use multi-aspect querying. We shatter the main query, like asking for the prototype of a mascot, into multiple subtasks. This ensures we check for dark image conditions, visual geometry, and orientation errors independently, guaranteeing that no critical tactical knowledge is overlooked during retrieval. But generic wisdom needs to be molded to specific live states, which is exactly what context-aware visual adaptation does. Using an experience rewriter, XSKILL takes a generic skill document and adapts it based on the live visual feed. So, instead of a generic instruction to fix an image, the injected prompt specifically tells the agent to rotate this specific upside-down image 180 degrees, applying precise tactical adjustments to the exact problem on screen. This approach leads to what we call empirical dominance on complex reasoning tasks. Evaluated across 4 backbone models and 5 different benchmarks, XSKILL consistently boosted performance over standard tool usage. Looking at the TIR bench results using the Gemini 3 Flash backbone, you can see a massive plus 11.13-point leap over the previous state-of-the-art Agent KB baseline. So, how does it drive these results? First, skills eradicate inefficiency. Structured procedural knowledge totally eliminates wasted reasoning steps. When we look at the specific error counts, the overall error rate dropped drastically from almost 30% down to roughly 15%. More importantly, specific structural errors plummeted, syntax errors were nearly cut in half, and toolname errors were virtually wiped out because the agent now strictly follows proven templates. Second, experiences drive flexible orchestration. Without experiences, an agent is overly reliant on generic tools like standard web search. But with XSKILL, it prioritizes complex, targeted tool chains. For example, on Visual Toolbench, code interpreter usage surged from roughly 66% to nearly 77%, and on Search Plus, specialized image search utilization spiked significantly to handle visual demands. Another massive breakthrough is zero-shot cross-model transfer. Because XSKILL externalizes knowledge into structured, human-readable formats, Markdown for skills and JSON for experiences, it isn't locked away inside parametric weights. This means a heavy model like Gemini 3 Flash can do the hard work of learning and instantly transfer that knowledge to unseen, smaller models like GPT-5 Mini or O4 Mini, boosting their performance entirely zero-shot. If we look at the evolution of agentic memory, XSKILL is clearly setting a new standard. Compared to state-of-the-art frameworks like AWM, Dynamic Cheat Sheet, and Agent KB, XSKILL is the only one that checks all the critical boxes. It's the only framework featuring dual-stream knowledge, visually grounded memory, and context-aware adaptation, and the only one with a true multimodal focus rather than just relying on text logs. In the end, this creates a training-free flywheel. Phase 1 handles distillation and consolidation, Phase 2 handles execution and adaptation, and every new task adds to the usage history, looping right back into our cross-rollout critique. This makes the system self-evolving, organically tool-agnostic, and completely training-free, meaning it achieves continuous learning and improvement without a single parameter update. Thank you for joining me on this deep dive into the cognitive blueprint.